This is an introduction to wave equation. I'll be explaining what is the wave equation and what is it meant for, and what are all the initial conditions or assumptions that are used in solving the wave equation. And also I'll be recalling the prerequisites needed for this solution of wave equation using the method of separation of variables. It is basically the Fourier series expansion and the Fourier cosine series or sine series expansions of a function. In wave equation, we look at the motions in a vibrating string. What we do is we will consider a string which is assumed to be an elastic string, so that there can be, you can pull it and release it, so that the strings will start vibrating. And of course I assume that the left end point, this end point, this endpoint of the string and the right endpoint of the string are firmly fixed to some wall kind of thing, or they are just tied to something. And so that you can see that this left endpoint and right endpoint will not move. Now, how to create vibrations in this string is, as I said, you can create the vibrations using potential energy. That means you pull the string like this, you just pull it at some point, you can pull it up and release it. So it will start creating vibrations in the string. Okay. Another way to do this, create this vibrations, is by giving it a kinetic energy. Like you just hit the string at some point using a stick. So okay, you just hit at this point using a stick. Then what happens is that due to the kinetic energy it gains, it will start vibrating. Okay, here we assume that each point of the string can move exactly upwards or downwards, like this point, and it has moved up, whereas a point here has moved down. So this is what we mean by the displacement of a point. So u is the notation representing displacement of a point, and it can be very well seen that the displacement depends on the position of the point from one end. This endpoint I am keeping as the origin. So from this endpoint you measure the distance. So this is the distance, means I call this as x. This distance is called x. So u, that the points, as I said, this point is moving downwards, whereas this point is moving upwards, right? So the displacement, it can be positive or negative. If it is coming down, it is negative, or positive if it moves up. So the displacement happening to the string is definitely depending on x. The displacement of the string definitely reduces as time passes. Therefore, u is a function of t also. So uxt is the displacement of a point. Since I am assuming the string to be tied at both ends, this endpoint, which is the point of the string at the position x, that is u0 t. That point will u means displacement of the point at a distance 0. That point will not be moving at any instant, right? So u0 t is equal to 0 always. As well as the right endpoint is also tied. So let the length of the string be L, then you can say that u at L comma t is also equal to 0. We also have mentioned that the string is said to vibrate by giving an external force, that may be by pulling it or by giving a force to some of the points of the string. So we also assume that these are known. That is, we take the initial position. Suppose I am releasing it from a height, or I am pulling it and releasing it, then the initial position may be something like this. This is the initial position. So this is a function of x, right? So that is taken as ux comma 0. 0 means initial time. I am pulling it up and releasing it. Then this function is the initial position of the string, and this will be denoted as f of x. So what we assume is the initial position is known to you. Okay. Similarly, I can set this string to vibrate by giving an initial velocity, and the initial velocity is dou u by dou t, right? The displacement's derivative with respect to time. So I represent it as ut at x comma 0. Time is 0. That means the initial velocity is known to you, and that is taken as g of x. So this is the initial velocity and this is the initial position. Most of the time what happens is we will be using either a potential energy or kinetic energy. So if you are pulling it and releasing it, your velocity, initial velocity will be 0. Whereas if you are hitting the hitting a string at its equilibrium position, then its position will be 0. One of them will be mostly kept as 0. Of course, you can pull a string and put a velocity. That's a different issue. But in usual problems, we'll be considering either the position or the initial velocity. If we model the wave equation using the partial derivatives, we can see that the equation that corresponds to u will be given by dou square u by dou t square is equal to c square into dou square u by dou x square. So this is called the wave equation. Okay, and I'm not deriving the wave equation here. We just use this wave equation and solve it. And while solving, we'll assume that the left hand point doesn't move. The right hand point also is not moving. The initial position is f of x and the initial velocity is g of x. So these 4 assumptions will be made use of while solving the partial differential equation. And we are assuming so many conditions that the string is a uniform string, and we are not consider the effect of gravity, and we will consider only one-dimensional vibrations. The string will be moving only up and down, not in this sideways. So that there are so many assumptions, and of course we learn all these assumptions while modeling the wave equation. To solve the wave equation completely, we need a little bit theory of Fourier series expansion. Now, suppose you consider a function f from the domain of length 2L, and we assume that it satisfies some simple conditions like Dirichlet conditions. Dirichlet first condition is periodicity. Second condition is it should not have infinitely many maxima, minima, and it should not have infinitely many discontinuous points also. In that case, that function can be expanded as a series of sines and cosines. Like f of x can be written as a0 by 2, where a0 is a constant, plus sigma n equal to 1 to infinity an cos n pi x by L plus bn sin n pi x by L. This n runs from, this n can be, both of these n's will vary, 1, 2, 3, etc. up to infinity. And the coefficients are given by the Euler formula. A0 is equal to 1 by L integral f of x dx, where this I am not writing the limits of the integral because it depends on the domain. If the domain is say minus L, then the integral will be from minus L to L, and the function will be the same. So that's why I am not writing the integral. If it is from 0 to L to R, then you have to write, in place of minus L to L, you have to write 0 to L. And an is obtained by 1 by L integral, say 0 to 2L or whatever be the domain of the function that is taken as the integral's limit. So 1 by L integral 0 to 2L f of x into cos n pi x by L dx, and bn is equal to 1 by L integral the same interval. If it is minus L to L, here also everything will be from minus L to L. If it is 0 to 2L, it should be, bn also should be having 0 to 2L. To solve the wave equation, we need two special cases of the Fourier series expansion. They are called half range series, or they are called the cosine series expansion and the sine series expansion. The importance of cosine series expansion is sometimes the function can be expanded as a series of constants and cosine functions. That is, here that bn part is missing, right? So there is only a half part of the Fourier series expansion. Whereas sometimes we'll be interested in the sine series expansion, wherein f of x will be represented as a series of sine functions. There will not be any cosine functions and constants also. So these two expansions are important. And for having this type of an expansion, the function should be having its domain equal to some 0, L2, and it should be going to R, a real valued function defined on the half range of the interval. In Fourier series, what you have to do is you have to take it from minus L to R, or 2L length, whereas the Fourier sine series and cosine series representations needs the function to be defined on a half interval, 0L type. Okay, and so f of x can be written as a0 by 2 plus sigma n equal to 1 to infinity an into cos n pi x by L, where a0 is given by the formula 2 by L. This 2 should be kept in mind because it was 1 by L in the Fourier series expansion. 2 by L integral 0 to L f of x dx, and here it will be always from 0 to something, 0 to L. L is the length of the interval, this. And an is equal to 2 by L integral 0 to L f of x into cos n pi x by L dx. Whereas the Fourier sine series expansion is like this: f of x equal to sigma n equal to 1 to infinity bn into sine n pi x by L, where bn is equal to 2 by L integral 0 to L f of x sine n pi x by L dx. So this is inside a bracket. Okay, this is all about the sine series expansion and cosine series expansion, which we will be using in the wave equations solutions.